Welcome to GoToWebinar, Web Events Made Easy. Welcome
Okay.
to the webinar. You have entered as an organizer and may
Oh,
now
I got
speak
it.
to any other organizers or panelists on the line. When you are ready to begin the presentation, press star 1 to allow all attendees to hear you. This system will notify you once you begin your broadcast.
Okay. I should be broadcasting. Sorry for the delay, guys, and a little technical difficulties. If you guys can hear me out there, go ahead and raise your hand, and we'll move forward. Excellent. We're live. Yeah, it seems like there's always a bit of a learning curve, so sorry for the delay. I'm going to jump in and start. Let's show the screen, bring up the PowerPoint, and good. Thanks for your patience. So I have the joke for the day. What is the difference between a designer and an analyst? And the difference is designers get second chances with their work. So, and then besides that little commentary, there's another pun for people that do CFD work. And for CFD work, where is that quote? I have it on my other screen. In CFD work, theory is when you know everything, but nothing works. Practice is when everything works, but no one knows why. In CFD, theory and practice are combined. Nothing works, and no one knows why. So hopefully mechanics will be a little easier than CFD. Today it's normal modes analysis, and we'll go through the basics, discussion of why it's useful. There's lots of stuff that normal modes is used for. It's probably, after linear stress analysis, it's the #2 most common type of analysis work that's done in the world. And it's all linear. How it works, some little details, principle of orthogonality, strain energy that kicks out, and mass participation. And then available resources, and our next training class is scheduled for October 15th to 19th, and it's already a go. We already have about 50% of the seats signed up. So if you're interested in training, that's your opportunity. Okay, come back here. Let's get out of there. This is linear dynamics. This is equation of motion. You start out with your mass times acceleration, times damping times velocity plus stiffness times displacement, and that is equal to your forcing function over time. And we've probably seen these in maybe our sophomore junior class in partial differential equations, and some engineering schools teach vibes during the bachelor degree, but typically it's a master's program. So, but the eigenvalue problem is introduced in PDEs, a sophomore junior class, and what you're saying is that there's no damping. Damping is removed, and there's no forces applied to the structure. And this is a pivotal point. There's no forces on it. And so when you run a normal modes analysis, there's no loads. It doesn't exist. And that should be your first clue when you see this equation that you don't have loads applied, that everything kicked out, all of your results, even though it's showing a displacement, a mode shape, it's fictional. It's just showing the relative displacements to the adjacent nodes. I like to think of it, it's a permissible mode of deformation of the structure. So no loads, and so it boils down, that's why they call it natural frequencies. It's how the structure wants to vibrate. And then it's just mass times acceleration plus stiffness times displacement, Ku. And when we do a linear analysis, of course, there's no acceleration, and we're just doing force equals Ku. But for eigenvalue problem, m times a plus Ku equals 0. And then you can assume a solution of the form, a displacement Umax sine Wt, and that's how it all drops out. That's where you get your stiffness minus your frequency squared, mass, and then you have your U naught equals 0, and then to not have what they would say a trivial solution, because you're saying is if U naught has, if you remove the U naught, then how do you get a trivial more than just zeros? You have to say that your stiffness minus W squared m is equal to 0. Giving us the well-known frequency relationship, W equals square root of K over M. And this is normal modes analysis. the fundamental equations, and it can be a wonderful guide. It tells you a lot. It tells you the frequency is proportional to stiffness over the mass. And these are little things people always talk about quickly. Yeah, just increase the stiffness, or conversely lower the mass to raise the frequency of a structure, and this is where it all drives from. Real simple. Okay. Why is it useful? Normal modes, it's a lot of places. Top here, this is a conveyor system, and that works by normal modes. You want to have the system to have one of its harmonic frequency in the motion of travel, so it has a natural free moving vibration. Or conversely, at times you want it to have no natural frequencies in the motion of travel, so you get no harmonics. You can go both ways. Drivetrain work, natural frequencies are everywhere in drivetrains. This is a sample holder for an electron microscope, and they want it to be very inert, very stable, not to be excited by any of the machine frequencies. Down here, this is a turret that's mounted onto an airplane, holds a camera system, and so this was used in a modal frequency analysis. Large transmission structures on this. This is an actual real model. This is one of the things that in FEMAP, when you're doing these web meetings, the computer in the background is processing, is actually compressing video and sending it out. So when FEMAP is trying to move stuff in models, it can be difficult. So like this model is 2.5 million nodes, and it moves a lot faster when it's not in video mode. And all the castings, tetrahedral mesh, plate elements, rigid links, and partial engine block. It was quite massive. And the goal on this is that the engine spins at, 1900 RPM. And so you want to avoid a frequency of 31 hertz. And the rule in industry is that from your computer model, you want to have the first mode frequency 20% higher than the engine frequency. And the reason they say 20 is because they don't trust the model. And typically, if they have dead-on data, they can say, oh, 10% higher than the first mode is good. But for modeling work, they want to see 20% higher. Okay, back to this. Then once you have a good normal modes analysis completed, then you can start leveraging it. One example is doing a power spectral density analysis, and that's common in aerospace. It's all over the place. Rocket launches where you have this white noise spectrum. You have all the frequencies combined, and they're all going all over the place. And it's used a lot for fatigue analysis, wind turbines, airflow over a wing, acoustic input from jet engine exhaust, earthquake motion, transportation, wheels over rough road, ocean wave. And earthquake analysis for vessels, really common. This is called a response spectrum analysis. And it's all based on normal modes. Once you have the normal modes done, it's just linear algebra. Modal frequency sweep. This is a headlight assembly. And it's what you're doing is you're building the model, connecting everything up, and then you're hooking it up to a shaker table. And we'll talk a little bit later about this. But all the basis is a normal modes analysis. And then in the automotive, which is one of the regions where Nastran is really popular, is all the usage in body noise, vibration, and harshness. So you have chassis, rough road, transient, engine vibration, wheel unbalance, interior nose acoustics, large eigensolutions, brake squeal. So this is why Nastran is so popular. The strongest solution sequence in Nastran is normal modes, solving these type of problems. So, okay. I advocate, if you're new to doing the types of analysis, do something simple. Do a pilot model so you can see it in action. And this is something I pull out in the class and say, okay, we're going to do the simplest model possible. We're going to do a beam. beam with a mass, something we can hand crank out of. That's just so simple. It's trivial. And so you have a stiffness, and you calculate the stiffness, 23,000, and the mass is 100, and you get this rad per second because it's a hand calc. And then you divide that around to get your equal to cycles, 2.41. And this model, just want to show it. Got to dig around. Don't want to make it too dry. Okay, there it is. Unable to know. Where did I say that? I got one of the things I got to check is that sometimes I have it open in another place. I'll open up this. Nope. Hey, like that. I actually did practice this. Okay. Voila. It's there. This model, I'm using a C-bush element. Now these models, I'm going to have these notes, and I'm going to have the models, most of the models I'm showing here, all in a package that you can download from the website. So if you want to see where this is going and practice on your own, you can. So this is a C-bush element. And I've told it to give it the stiffness in the vertical direction, which is the Y, 2300. No stiffness, more or less, in the opposite directions. And then super high stiffness in the rotation. So it has six degrees of freedom. And then it's just a mass element tied out to the end. So, and let me delete this. I'll show you. New, normal modes, eigenvalue. That's it. Oh yeah, and it's constrained right there on that end with 6 degrees of freedom. It takes longer to load the solver and crunch through things than anything else. And the results it kicks out, it has these low frequencies here, which is logical. You go right click, animate. Because remember, those are the stiffnesses that we gave at 1. And here is our 2.43 based on theory. And it only kicks out 3 modes. And the reason that is only 3 modes is the mass, there's only mass defined in you think of it as the 3 displacement directions. There's no mass associated with rotational degrees of freedom, which are the IXX, IYY. So if you were to fill these in and actually give it some mass in that direction, I'm just making this up, then you rerun it, you're going to come back with 6 modes. And I was a little unsure when I first did this, so I just built this model to prove it to myself. And there's nothing like having your own little treasure chest of proof models of things you just built to prove things out. Simple, easy to do, validatable. So good. Back to the slideshow. I should say something verifiable, because verification is where you're checking your work against hand cranks, and validation is when you check your model against experiments. So when you're modeling, that's where they say always have something where you're verifying in sections, small things to build sort of a picture. So that takes care of that. Moving on, principle of orthogonality. And this is a little hiccup that comes along and that catches people when they're doing normal modes work, is that they see these compound modes together. And let's bring up that model. Open, simple beam, pin connections, like that. And same thing, normal modes analysis. And when you do a normal modes, it'll come up with this screen here. Nastran normal modes analysis. And I'm going to ask for 10. And I'll hit analyze. And you guys will see this at times. And this is a 0 mode. This indicates a rigid body motion. And you're going to get this mode shape, and it means nothing. Remember, it's just moving in space. And that makes sense, and although it's shaking like that, it can be a little bit deceptive because what it's really doing is drilling. See, we have a pin connection there. So it's still free to rotate down the axis. Think of it like a drill, and you're drilling around like this, and that mold shape is just sort of an artifact of that unconstrained motion. So since we're here, and since this is not a demo, this is for learning, we'll go down pinned, okay, constraint on node like that, okay. Now, let's just take one node on the end, and what we want to do is we want to constrain it in the Rx like that. And we'll just combine. Control G to bring that back up. So now it's not allowed to drill down the axis. Done. And you can see it got rid of this zero mode here. Now we're at 386. So this is just standard practices. If you have rigid body motion in your structure, all systems, all structures have 6 degrees of freedom. Think of it like a satellite in space, that it can move, translate in 3 degrees of freedom, and it can rotate in 3 degrees of freedom. And when you do a normal modes analysis, all your unconstrained mechanisms, rigid body motions, will have near zero frequencies. And this can be a great debugging tool for running your models, and you have singular matrices if you have a standard static linear stress analysis, and it kicks back and it says you have mechanisms and pivot ratios. If the model is not gigantic, it might be faster just to run a normal modes analysis and find out where the mechanisms are in the model, where things are unattached. Here's the first mode, and you see you have another mode right on top. And let me put on in view like that, X right. And you can see it moving in that plane like that. Okay. Now let's switch to this other mode at right angles. And almost at right angles. A little bit tricky, but what it's doing is that in a beam structure like this, it really is, if it wasn't just showing these two modes, you could have a near infinite number of modes in 360 degrees, because that's really how it can vibrate. It can vibrate any sort of in plane of that rotation. Numerically, they just reduce it down to, they just give you two modes, the two orthogonal modes. And this will occur anytime you have symmetry. Like this, you get these orthogonal. It works, and it works great for a simple beam. And when you get to the higher modes, it all breaks down because things start to going apart. But like for the simple bending. So it's just something to note, and it's a good check for your model too. If you know the model is symmetric, it's a cylinder or something like that, then you should see these double modes. And if you don't, then that means something is probably wrong with your model. And this goes into, this just sort of looks at when you run a normal modes analysis and things get kicked out. You get all these things that come from the analysis, and one of them is strain energy. And what do you do with it? And there's not a whole lot of information out there that says, wow, this is really useful stuff, and this is what this is what everybody does it. There's not exactly a primer on engineering vibration analysis. And so on strain energy, when you run a normal modes, again, there's no forces, so well, really there is no classic strain energy because there's no forces. But what does get kicked out is the relative displacements. And if you have relative displacements, you can get relative strain. So then you could say, well, some parts of the structure are going to move more than other parts, and you're going to have localized movement that's greater than other places. And so you can convert this into a strain energy is what they classify it as. And all it tells you, very simply, is that where parts of the structure are deforming more than other parts for any particular mode. And the usefulness is that you can look at the strain energy over in this model. It's a bracket, and you can say, well, we really need to increase that first mode frequency. The first mode frequency is causing us problems. In this sense, it was for a seismic analysis, and we needed to move it higher, get it above a certain threshold. And the simplest way was to reinforce the bracket in areas of high strain energy. So if you attack the regions that have high strain energy, to lower those regions, you're going to increase the frequency of that first mode. I hope that makes sense. It's what you're doing is you're locally addressing the problem. You're not hitting it with a sledgehammer. You're pinpointing areas that you want to reinforce, and that's the utility of the strain energy approach. Okay, so here's the model, and it's just a very simple thing. And let me, I really like this new setup. I'm going to pick on property right here, right-click, visibility, show selected only. Well, you guys saw that. That's under the selector entity. You turn that on. So now it's looking for properties. And I have it set on the selector mode just for select single item. And so it hunts. And when it finds it, you can see the cursor is highlighting there. Right click. This was added in, and I'm not sure whether it's version 3.1. So, and then you get these options here. And so this bracket went through several iterations of reinforcement, and we were looking for high strain energy density. And these blue regions here are just telling you the strain energy is so low it sort of fell off the cliff. It just wasn't, they just don't report the values because they're near zero. And then, of course, you get these high regions around here, and if you wanted to take it to the next level, you would want to reinforce this region right around the clamp or make it thicker through here. But we reached our target, we just stopped. So let's look, where do you request strain energy? Go down through here, master, output request. Right there. That simple. You just request that it gets dumped out, and you're going to get crazy numbers. The numbers just go all over the place. If you look at the strain energy, it's where you get 28 point. I have no idea why, 28.67 or 0.02. The way I treat it is I'm just looking for relative. I'm just looking for changes between it, and I don't give any importance to the magnitude because there's no forces. So the magnitude, who knows? Doesn't mean anything. It's like the deformed shape. And this is the function that's once you get the design you like, you're running a response spectrum analysis, and this is your input, and you're inputting acceleration versus frequency, and it's just using your normal modes. So let's go back, and I want to mention that if you guys are doing this sort of work and have questions, give us a call. We're more than happy to share what we know, and we do have tutorials on our website for response spectrum analysis, power spectral density. We're redoing our PSD tutorial at the moment, but the old one, perfectly fine. And we also do quite a bit of modal frequency analysis work, and so we can answer questions for you. There we go. Mass participation in frequency sweep analysis. Let's find out where that. I'm going to have to close some things. You can see I get carried away with tabs. Close that. Come back here. Radio frame. That was a fun project. Nope. 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 Simple beam. No. I thought I saved that. There it is. Ducato. We got involved with doing a bunch of headlight assemblies, and it's interesting. They're really complex stuff. So this is for Fiat, and there's the mesh outline. Very careful paving, using the whole skill set of getting meshes lined up carefully. And, nothing's perfect, but a lot of this stuff just sort of goes along for the ride. And anything important, like this is the base pattern in the back, you're quite careful in meshing. And you run through the normal analysis, and then the requirement on this is that they put it on a shaker table, and they shake it from 0 to 200 hertz. And then so what you want is a structure to be resistant to that modal frequency sweep. And you run the modes, and you get this at 42 hertz. And that's an interior reflector that's just not quite constrained. I mean, it is what it is, and that's the way it moves. And so that was the subject of several redesign work. And so you get your frequency range here, but it doesn't tell you the relative importance of each frequency. It doesn't tell you which sort of carries the most mass and what is doing what. And so this is where you request it to dump out the mass fraction. And without mass participation, with mass participation. So let's go there. Options, modal buckling. This is where, and if you guys have done any vibe work, you're going to see this come up. You may wonder. So what you're requesting is for the program to tell you how much mass is associated with each mode. And it will tell you exactly, what is the dominant mode and how much mass is associated with that particular, how much of the structure is moving with that particular mode. And a rule of thumb in Vibe is they say, they want to just throw this out. The first 3 modes are the most important. That's where your dominant mass, occurs. And you sort of wonder about where they get these, homilies like that. And it really derives from when you look at frequency equals the square root of stiffness over mass. And when you run a normal mode analysis, it's going to sort it the lowest mode first. It doesn't sort it by the mode that has the most mass, the most energy associated with it. It's just the lowest frequency. Kicks it out. And so given that, when it's calculating this, sometimes you can have in structures where you have low frequency modes that don't have that much mass associated with it. They're not high energy. The reason I'm saying energy is because the mass determines how much energy is in the structure moving that direction. And when you think about damage to structures, it's the amount of mass associated with that frequency that's going to cause the damage. It's the amount of force. F equals ma. And so in natural frequency or normal analysis, it's the mass that kills you. So this is why it's useful looking at where mass is associated. And in this structure, if you look at the z direction, vertical, being shaken up and down, that's one of the really important ones on the shaker table. And it'll kick out these functions over here, and you can of course plot them. And this is your fraction of mass associated with each mode. So your first mode here, you have less than 10%. Your second mode, you have 25%. So this is telling you your second mode is far more important than your first mode. And when you do your modal frequency analysis, it tells you want to expand on the second mode, that this is where the damage is going to come about. And then you can also look at the sum through here, and it shows how the mass adds up, and you get up to about 86% when you're out 35 modes. So this is capturing the mass of the structure. And a lot of vibe specs will say, run your, sum up your modes up to 90% of the mass of the structure. And that's actually an ASCE, American Society of Civil Engineering code for doing earthquake analysis, is that you're going to have 90% of the mass of the structure in the analysis. So, and likewise, you can do the same for the other modes, like that. And so when this model here, it can be a little deceiving on the mass fraction, And so I want to step back, go back to our simple beam, not here, simple beam, principle orthogonality that we just ran. Okay, we didn't ask for anything on mass participation. So now let's go back in and request it. Okay, I'm just going to ask for right there, these just 2 items. Modal effective mass fraction, analyze. Dumps out. I'm going to expand that out. I'm going to look at the FO6. I'm going to do it old school way first, and then I'll show you the more easier way to do it. This is what it dumps out in FO6, modal effective mass summary. And it says that here we have in the T1, we have near 0, and that's going in the x direction. And the T2, which is vertical, which is moving, look at this, you're at 97% of the mass. And likewise T3, which makes sense. Remember, I only asked for 10 modes on it. And so it's just not anything actually moving down the axis of the tube. It's just not picking up anything. But of course, since it's bending, because it's pinned, look at it, it's picking up 97%. And here, if you sort of squint your eyes and try to read, you can sort of pick out your fraction and your sum. It's a bit hard. I used to do it like that before I got comfortable with looking at the mode. So remember, x is down. We don't want anything to do with that. So let's look at fraction right there. And this is the default legend. So you can see the first mode, you're capturing 80% of the mass of the structure. It is hugely dominant, the first mode, second and third. And likewise, we'll probably see something very similar for that. So, woohoo! So the first mode here, we're not getting much, but remember we got the principle orthogonality, and so that it's sort of like, you consider the first 2 modes the same. So you're getting the same. You're getting even a little more, 88%. So it is a very, very useful thing. I sort of can't, if you're doing vibe work, it's really helpful to look at where the mass is going to. And also the mode shape. A lot of classic people will just look at the mode shape, because only loads in the direction of the mode shape are going to excite it. And that's another concept. If your loads are right angles to the mode shape, they have no effect upon that mode. It's like, no, you get a free pass. And this is where it's useful to look at the shape and also look at the direction of your applied loads, because you may get a free pass. Because some people say, oh no, we have this load that's operating at 20 hertz and it's going this direction. And you look at the structure and you say, well, geez, even though we have a mode shape at 20 hertz, the mode shape is moving at right angles to that load. So it's null and void, which can be real handy. But then when you tie that in with looking at mass, you can also say, well, gee, we have this excitation, function, this load, but it's at a frequency where the natural mode of the structure has very little mass associated with it. Therefore, this applied load will cause very little damage. So that's another concept. Okay, I'm doing on time. I think I'm just about right. I look at my. Oh, good. I sort of like to keep these at 40 minutes and around that. So I want to talk about optimization. It's a very popular topic because people, when analysis is required, why does it take so damn long? And this is, I think this is a popular refrain from anybody outside of the analysis world is, when you have to do mission critical analysis work, it's required. You have to do it, meaning it's a real model. And if you're not actually doing the work, anybody standing outside is, why does it take so damn long? And isn't there a computer program that can do it for you? And this is the siren song of optimization. Is it, we'll just let the computer figure it out, and it won't take so damn long. And I had this just great project. This is just, it just went on and on. It was Where did I stash it? There. This is for a paper mill, and this is a forming board where there's a wire mesh that goes over the top with the fibers. You know, they're making paper. So it's all in this wire mesh, and this forming board goes over here, and they pull a vacuum down here in this box. And so it sucks off water off the mat, and then all the cellulose fibers trundle onto the big drums and get pressed into paper. And so this is in the industry, this is called a forming board, and they put ceramic tiles on the top and stuff, and the mill operates at around 11 hertz. That's the rotational frequency. So, and they know from practice that if the frequency of this board is below 11 hertz, if this moves below 11 hertz, then it'll get excited by the wire mesh going over the top. And then once this forming board gets excited, because this is 30 feet long, so once this thing gets moving, it'll tear the machine apart, the paper mill machine apart. So it's really critical that it has frequency higher than 11 hertz. And all stainless steel, big structure, really expensive. And we just beat on this till it just went on and on and on. And it was tricky. It's long, and and you have this forming. We were trying to figure out, and stainless steel it's expensive, big, and it's a classic thing. It's your frequency is the square root of stiffness over mass. Anytime we try to add, we made the thickness here, it added so much mass, the frequency just went down. And I'll show you what I mean. Is we'll just jump in, new. It remembered from the prior that I was doing normal modes. And we were throwing things back and forth, and trying to figure out. This would have been a classic example of somebody said, well, gee, don't you have an optimization program? I got to set it up, deform style. And I'm going to, when you do normal modes, I always do percent of model, 10%, like that. So there's our first mode, 8.4. And we screwed around with it for a long time. And I'll show you what I mean. Remember, that's 8. So let's just say, well, gee, it's moving up and down. It's like a beam. Okay, fine. So then let's just reinforce. I will just make those right there. You know, this. I want to make sure I got the right plate right there. Edit. You know, that's 8 mil. So we'll just make it half an inch, 12.5. Body plate right there. So let's just rerun. This is a real model. You see, 5,000 nodes. Crazy. There, the new mode, 8.3. It went down. Oh, that was great. That was useful. I'm going to undo. So I want to make sure I have messages turned off. Good. So this went on probably about a week, and we weren't getting anywhere until we thought about the mode shape, and we really just started thinking, well, look, it's a beam, it's going up. What we need to do is reinforce that beam. And it was just sort of blind. I don't know. I mean, it just kept looking and looking and said, why don't we reinforce the top and bottom, you know, with some thicker ribs? So we put in this structure right here, and let me show like there. So we put that inside the column to reinforcement these rods. And right now they're quite thin. I did that on purpose, and because it makes this. And they ended up being inch diameter rods, and there, Control G, there we go. Right click, show all, like that. Now let's rerun. And the first mode, 13 hertz, like that. And this the same way. You can look at mass. You can look at the mass participation, and it's quite useful too, because it just confirmed where. Oh well, I'll just take that. And go into functions and the direction of interest. Let's look at y going up. And you see the first mode is dominant up there. You're close at 48%. And that is why the first mode was so important on this structure, because it had so much mass at near 50%. And so of course once that first mode got going with all that mass, it just tore the machine apart. So this was a real design. Actually, that's the way they went forward with everything. But what I like to say, it really shows that there's just no way an optimization program would have figured out to put a rod in there like that. And I don't even know how you would start, because the structure has so many design constraints to it. Design requirements, what you would do with it. Okay, but saying that, occasionally, there's structures that do work for optimization. There's lots of little examples. This is the optimization program inside FEMAP, Tosca Optimization. And this is sitting around, and you guys, I'm sure, have seen this. Let's go switch over to, it's embedded in static. And I'll just go through. I could jump to it, but I get lazy. Right there. This is the Tosca program for setting things up. And maximize stiffness, and you can also do vibe. Maximize eigenfrequency and reduce volume. It is in there. It's an add-on option, but it does do optimization. And you have all the standard, documentation, how to set it up. And we've played around with it and done a few models. Honestly, we haven't found anything that commercially we've been able to use it for, but I know people out there use it. And this is just examples. You take a plate, carve it out, you get a cool design. And, freeze elements around hole. This is a casting, carve away, and it'll do solids. Except the demo, I think they just use plates because they can actually build these models and run them in their lifetime and symmetry. And you can do it for, stress and vibe. So if that's of any interest to you guys, give us a buzz on that. Oh no, I lost my, there, come back here. Dun, 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 dun. Where are we? Getting close. Hey, last slide. I have this little white paper on linear dynamics. It's a basic tutorial. It was, I learned a lot when I put it together because I had to boil everything down and base it in as with few as equations as possible. So that's for download. There's also a lot of good information just within the installed help thing under NX Nastran. NX Nastran 8 help. I always go to the PDF. There's Basic Dynamic Analysis User's Guide. That has a lot of good stuff. Fundamentals, equations of motion, velocity, acceleration, single degree of free, and nomenclature. This is a great place to start if you're going to get into learning this stuff. There's no excuse for, well, of course there's an excuse, but it's like doing your homework. When you're trying to learn something, you can only do so much lecture where you sort of have to go off on your own and just ponder things and do homework, do your own work. And you guys may have noticed it when you call for tech support. If we feel that this is really, you're calling in is something that requires homework, we'll often direct you to go look at one of our tutorials or something like that, because it's really for learning. If you force feed the information quite fast and you just verbally tell them, it's tough. The retention time is pretty low. It's better to sort of go at it from different angles. There's also one other thing I want to mention. I'm going to put this also out with the package. Technical library, predictive engineering course notes, because I want to put this with this linear vibration. It's this thing here. This I actually got many years ago. You see UGS, but wow, it's 255 pages, and it just goes through Nastran dynamic analysis, review of fundamentals and dynamic single. It would be the foundation for a whole year graduate level of linear vibration mechanics, all the 255 pages. So I'm going to put this in with the package on the linear vibe. So I've been going so fast, I haven't checked to see if there's any questions. I know Adrian is here. Adrian, are you on? Do I have any questions I need to answer?
No, actually it's been pretty quiet. We had one with the beam model up front, just wondering if we had a massless beam.
Yes.
But no, it's been a quiet webinar.
Yeah, no, it's like pure here. Let's just go hard theory. But here, you guys have definitely enough ammo that and buzzwords that you could definitely participate and fool probably 90% of your peers that do analysis all the time. You just have to say, just when someone presents a normals analysis, just say, hey, have you checked the mass participation of those modes? And hey, how does the strain energy look in that structure? So you got the full breadth of buzzwords, and we're more than happy if you guys have follow-on questions after this. Is give us a call, send us an email, and we'll go through it, because it's really just it's probably a good 20 to 30% of our work at times, sometimes 50% or more. So that's it. I'm going to close it out. It'll be posted on the web and during the next week. Thank you very much for your attention, and have a great day.